you looked at differentiability, you'll see that it will say something along the lines of a function f of x is differentiable at x equals a if the derivative exists at a. So it'll say something along those lines. And in single variable functions, your derivative existing and your function being differentiable are the same thing. But it becomes a little bit blurry when you're dealing with two variable functions of two variables, because at any one point there are infinitely many derivatives. Think of standing on the side of a mountain. What's the slope where you're standing? Well, it depends what direction you're facing. So you've got direction-dependent slopes, direction-dependent derivatives. And your two partial derivatives are two special cases of those directional derivatives. The one where you're facing in the direction of increasing x, and the one where you're facing in the direction of increasing y. So those are your two partial derivatives. And anti-intuitively, sometimes you can have a function that is not differentiable at a point, even though both the partial derivatives exist at that point, which is really bizarre. But you can think of it, again, if you think of it in terms of standing at a spot on the side of a mountain, perhaps if you face in the one direction, you've got a perfectly ordinary kind of slope in front of you, and you turn 90 degrees and you still have a perfectly ordinary slope in front of you. But if you were in the middle between those two, maybe there's some horrible crack in the ground, or there's a cliff right in front of your feet or something. And so your function is differentiable in those two specialized directions, but not outside it. Sorry, I realize I haven't plugged the microphone in, which is probably fine right now because I'm standing over the tablet, but it won't be as soon as I move away. So just excuse me while I do this. Let me pause the recording. Okay, microphone in. So what I'm going to do now is I'm going to demonstrate. Now, we haven't actually dealt with differentiability yet, but I'm going to connect again with single variable calculus. Differentiability requires continuity. For a function to be differentiable, it has to be continuous. And you saw that back in first year. If your function is discontinuous, if it's got a hole in it, or if it's got some big jump discontinuity, then it's clearly not differentiable at that point. Things get a little bit more complicated when you're dealing with multivariable functions, but that basic premise still holds. Differentiability is the stronger condition than continuity. In order for a function to be differentiable, it needs to be continuous, and that relationship holds even with multivariable functions. So I'm just kind of telling you that on faith, but I think it makes sense. If you've got a hole in a curve, your function, you can't work out your slope there because there's nothing there. And same thing if you have a surface. If you have a hole in your surface, you can't work out a slope where there's a hole. Similarly, if you have a jump discontinuity in a function, so your curve wiggles along and then there's a jump to somewhere else, you can't ask what's the tangent there because you can't draw a tangent to some place where there's a jump discontinuity. Same thing with surfaces. If you have a surface that has some sort of crack in it and there's actually a big gap between one bit of surface and the other, you can't work out the slope at that gap. So let's have a look. What heading am I doing today? It's still some partial differentiation stuff, but also differentiability. So tangent planes, differentiability. Okay, so first of all, I'm going to demonstrate that it is possible for both partial derivatives to exist and what does it mean to exist? It means equal to a number. The number could be 0 or 1 or pi or negative 10 or something, but frankly not infinity. For a derivative, if your derivative equals any real number, then we say the derivative exists. Yet for the function to be discontinuous. Oh, discontinuous, yes, discontinuous, but that's not actually what I'm focusing on, not differentiable, to be not differentiable. Because not continuous. So what I'm trying to do here is I'm trying to break apart those two ideas, differentiable and derivatives existing. Because in single variable functions, they were the same thing, but in multivariable functions, they are not. Okay, so the example that I'm going to demonstrate that with is it says continuous function. So here we have a piecewise defined function. I think this must be our first piecewise defined function of the course, but it's not by any means the last. Okay, so where x and y are both 0, so the origin, my function is defined at 0, as 0. At any point other than the origin, my function is defined as that funny rational expression. All right, so what I'm going to do, so this is a piecewise defined function. Piecewise defined functions always have the potential to not be continuous. They always have that potential. Because your function is divided into two pieces. And do those pieces match up? I'm deliberately using fairly vague, non-technical language here because I'm trying to be generic. But as soon as your function is piecewise defined, there's the possibility that the two pieces don't match up in some way, that there's some sort of break between them. And as soon as there's the danger that your function is not continuous, there's simultaneously the danger that your function is not differentiable, because a discontinuous function is not differentiable. Whenever differentiability is in doubt, you have to differentiate from first principles. So what I'm going to do now is I'm going to work out my two partial derivatives at 0, at the origin, but I have to do it from first principles. I can't use my differentiation rules. In other words, I can't use quotient rule. I've got to use first principles, so let's do that. I'm going to work out my first derivative, my x derivative at my origin. Limit is h tends to 0 of f of 0 plus h 0 minus f of 0 0 over h. Okay, whenever you are... So in this next line now, I'm going to actually put in my function. Whenever you have a piecewise defined function, slow right down and make sure that when you are using your function that you're using the correct piece of your function. Because if you mess up at this stage, you've messed everything up. Okay, so that first expression in my numerator has an x component of h and a y component of 0. H is tending to 0, which means h is non-zero. So for that first term in my numerator, I'm interested in the top piece of my piecewise defined function. Okay? And let's have a look. My x is h and my y is 0, so that will be... That'll be 0 minus h cubed over h squared plus 0. Minus f of 0, 0. X is 0 and y is 0, so I want the second piece of my piecewise. Okay, now I really belabored that, and you might think, gosh, Tracy thinks we're very dim if she thinks we don't know how to read off piecewise defined functions. Sometimes it can be quite confusing. Sometimes it can actually be quite confusing which piece you want. So do yourself a favor and slow down and make sure that you're reading off the correct piece. Okay, let's tidy that up a little bit. Lim h tends to 0, that'll be minus h cubed over h cubed, and that's the limit of minus 1, and the limit of minus 1 is minus 1. I don't need to think what happens as h tends to 0. H could be tending to 0, h could be tending to pi, h could be tending to infinity, it could be tending to negative 1,000, h can tend to whatever it feels like. The limit of minus 1 is minus 1. So I never actually did consider what happens as h tends to 0. Okay, so my x derivative exists. My x derivative is equal to minus 1. How about the y derivative? Similar story. In fact, let me see if I can squash it in on this side. The y derivative is going to be the limit as k tends to 0. You can use h again if you feel like it. I just like to use k for the y derivative. And now it will be 0k. There we go. Once again, so let me scroll up. There we go. F of 0k, let's think. X is 0, but y is not. Therefore, I want the top piece of my piecewise defined function. I plug in x equals 0, I plug in y equals k, and I get, 0. I actually get 0. In fact, just so that somebody reading these notes knows exactly where that 0 is coming from, let me be quite explicit about this. And then f of 0, 0 is 0. Okay, you didn't need to write out all those little bits. I'm just trying to make the notes very clear to somebody who can't make it to today's lecture, because I would say we're probably about half a class, aren't we? Maybe slightly more than half. No, we're more than half. Oh, it's because it's cold. It's not cold. This isn't cold. I mean, I realize Cape Town doesn't get down to 0 or anything, but honestly, this isn't cold. Cold. It's slightly damp and it's moderately warm. Sorry, Durbanites, maybe to you it's cold. Okay, so this is the limit of 0 and that's 0. Now here is something that I know bothers people. I do not understand why it bothers people. Please keep quiet, but I know it does. Please keep quiet. My x derivative and my y derivative are different from one another. This is not surprising. It's not surprising at all. Come back to my analogy of standing on the side of a mountain. Do you expect to have the same slope when you face one way and then when you turn 90 degrees and face the other way? No. But I know it bothers people when these derivatives are not the same. Every single test and exam, every time I've taught this course, there's been somebody who said, like, the function's not differentiable because these two things are different. Or the function's not continuous because these two things are different. The fact that those slopes are different is, I'd be more surprised if they were the same, really, than if they were different. Really not a big deal. Different is fine. What we're looking for is, do they exist or not? They're both equal to real numbers, therefore they exist. So I'm actually going to write here. Do not be concerned that these are different. Oops. Come on. That these are different. It is not surprising. Okay. As I say, I don't know why that concerns people, but I know there's always some people that get really bugged by the fact that the derivatives are different, but it's fine. Okay, cool. So what? What am I trying to demonstrate here? I'm trying to show that my function is not differentiable by showing that it's not continuous. Approach 0, 0. X equals 0. Let's approach 0, 0 along x equals 0. So I'm interested in the limit. Please keep quiet. Please keep quiet. If I approach 0, 0, so let me draw a little domain picture. Okay, this is the point that I'm tending to. So I'm approached along x equals 0, that's my y-axis. So there was path number 1. Okay. I'm going to approach along y equals x. Approach 0, 0 along y equals x. Okay, so I'm going to have the limit x tends to 0, 0. And now I'm going to replace all the y's with x's. And what do I have? I have x squared minus x cubed over x squared plus x squared. Okay, I'm going to divide top and bottom by x squared. If x is tending to 0, by definition it means x is not 0. So that's 1 minus x over 1 plus 1. And that limit, if we allow x to tend to 0, not equal 0, tend to 0. If we allow x to tend to 0, that limit becomes, well, the x term gradually fades away, and our limit is 1 over 2. Our expression is never equal to 1 over 2, because x is never equal to 0, but our expression approaches 1 over 2 as x approaches 0. That's what limits are. Limits are what are you approaching. Okay, so now we have a contradiction, because if we approach along the y-axis, it looks like if a little ant were walking along the surface vertically over the y-axis, it would be convinced it was heading towards z equals 0, but a little ant walking along the surface over that y equals x line, or under, depending what the surface is doing, would be equally convinced it was tending to z equals a half. Our limits disagree, our function is not continuous. These results disagree. Our function is not continuous at 0, 0. Continuity is a necessary condition not sufficient, but necessary for differentiability. Hence the function is not differentiable at 0, 0. Okay, so the big deal here is so this is the big deal here. The partial derivatives is not enough to conclude differentiability. Okay. All right, and so we decouple those two ideas of derivatives existing and differentiability, which in single variable calculus you can't decouple, but in multivariable calculus you can. Okay, everybody happy? Basically, warming up the water so that we can jump in and talk about differentiability now. Question at the front. That I have to differentiate from first principles. It's a piecewise defined function. Any piecewise defined function always has the danger at the join between the pieces of being discontinuous. And here the join between the pieces is just the origin. But at the origin there's the danger of discontinuity. And as soon as there's the danger of discontinuity, it means there's the danger of non-differentiability. And when differentiability is in doubt, you have to differentiate from first principles. Otherwise, you might get the right result, but you might get the wrong results. You can't trust your differentiation rules. You've got to do it from first principles. Okay, and we're heading into a section that's all about differentiability. You're going to be doing quite a lot of first principles that look very similar to what I just did. Okay, use your differentiation rules. You can't trust your answer. It doesn't necessarily mean your answer is wrong, but you can't trust it. Question? No, you can't. No, you can't. So the question is there any way you can use squeeze theorem to show that the limits are not the same? So basically, to come to the same conclusion that we did with this partial approach thing. And you can't really, because you can sit there with your squeeze theorem. So if I try to do squeeze theorem with that, If I'd written whatever that thing is, xy minus x cubed over x squared plus y squared minus 0, stuck it between some absolute value signs, the greater than 0 I get free, but the smaller than, I now need to sit and I need to design something to go on the right-hand side that's bigger than what's on than the middle expression in your squeeze inequality expression. And that it's got to fit those three criteria. It's got to be bigger. You've got to be able to work out its limit. And the limit has to be 0. You're going to fail. You're going to absolutely fail to create such a thing because you're trying to do something that's impossible. But the problem is you're never going to know whether it's because what you're trying to do is impossible or whether it's just because you're just not getting the squeeze theorem right. Because squeeze theorem's tricky, and sometimes the limit does exist, and yet you still struggle to use the squeeze theorem. So the simple answer there is no. You can't use squeeze theorem to prove that a limit does not exist. Question?
I was just wondering why we did the partial derivatives and why we didn't just do the approach along the...
Because what I'm trying to demonstrate here is not the discontinuity. What I'm trying to demonstrate is that your partial derivatives can exist even though your function's not continuous. Yeah, which seems really odd because.
The question was just like see if it's differentiable, then we just do the approach along.
Yeah. If you were just trying to see is the function differentiable, showing that it's discontinuous would be good enough. But that wasn't what I was trying to demonstrate in this particular exercise. Okay, let's move on. I'm going to jump page because I'm almost at the bottom of this page and I'm starting a new section. So here we go. Differentiability and tangent planes. I'm going to mix that around. Tangent planes and differentiability. Okay. A curve has tangent lines. Surface has tangent planes. I suppose the surface also has tangent lines. If you're standing on, or if you're looking at one spot on a surface, there are infinitely many tangent lines with slopes that match those infinitely many direction-dependent slopes. But all of those tangent lines together, if you just picture them all and sort of sweeping around, those tangent lines together define a tangent plane. So the tangent plane is the sort of geometric equivalent, or sort of concept equivalent to tangent lines on a curve. Now, any plane, if you think back to first year vector geometry, if you wanted to find the equation of a plane, you needed one point, any point, and you needed two direction vectors that were lying in your plane, in the plane of your plane, as it were. Sometimes you'd get those two direction vectors by starting off with 3 points. So you start off with 3 points and then you subtract them in pairs to get those two direction vectors. Those two direction vectors need to be non-parallel. Otherwise, they only really count as one direction vector. So you need two non-parallel direction vectors which you would cross to get a vector orthogonal to your plane, and that vector orthogonal to your plane is your normal, and that would give you the coefficients of your x, y, z in your plane equation. Okay, so our tangent plane on a surface, it's a plane like any other plane. In order to get its equation, we need a point, and we need two direction vectors. So what we're going to use is the point of tangency and the two partial derivatives, and then we can get our plane equation. Okay, so uniquely by a point and two non-parallel, two non-parallel direction vectors. A tangent plane can therefore be found using the point of tangency and the okay. And a little bit of fiddling, just using your knowledge of first year vector geometry. The equation of the tangent plane at some point, x naught, y naught, z naught, is this thing here. Okay, and I want to draw your attention to the similarity of that formula to your straight line formula that you'll have done at school. Now, the very first time you ever see an equation for a straight line at school, you're probably given y equals mx plus c. That's that sort of straight line equation. But you quite soon after that learn another one, which looks like recall school geometry. You can find the equation of a line with y minus y naught equals m x minus x naught, where as soon as you learn some calculus, that m could be worked out as f dash x naught. Okay, so that should look familiar from school geometry. I hope it does. See how this tangent plane equation is basically just added one more term, but one more term that looks just the same. We're just adding another dimension, orthogonal to the first one. So really, this is just like your straight line equation, just stepped up a bit. Okay? And in fact, later on when we do Taylor's theorem for two variables, this has links with that as well. So you might want to leave a little note in the margin or something saying see Taylor's theorem, which will only really make sense when we get to the end of the semester. But of course, you're keeping your notes forever, aren't you? So it might not make sense right now, but give it a couple of months and it'll make sense forever. Okay, so this also has links with Taylor's theorem because the Taylor expansions are all about a Taylor expansion of a function is about approximating a function with a polynomial expression. And if you chop away all of the terms except for the linear terms, the linear and constant terms, you're approximating your function with something linear, and that's what a tangent plane is, and that's what a tangent line is. It's the linearization of a function. So these are basically the first three terms of a Taylor expansion of a surface. Oh, and so, a few things. There we go. Let me actually write. There's also links. There's also links to Taylor's theorem. But also, what was the other thing I wanted to say? Oh, okay. We'll see an equivalent formula expression, let me say, using grad. And again, that might not make sense right now, but in a week or so's time, that will make sense. Okay. Yeah, I'm just going to demonstrate an example. There's much more to say about tangent planes. I'm going to do number 90. Number 90 says, find the tangent plane to z equals... sorry, I must... I'm actually a fairly well-behaved stylist this semester. Sometimes it can be... Yes, there was a question? Oh, thank you. Okay, please be quiet. So let's evaluate the two partial derivatives. The dz by dx will be 2x e to the x squared minus y squared. Please keep quiet. dz by dy will be minus 2y e to the x squared minus y squared. Okay, I want to evaluate those two derivatives at the point 1 minus 1, 1. X is 1, y is minus 1, so my numerator is 1 minus 1, so it's e to the 0, and e to the 0 is 1, so it's just 2. Oops, sorry, I wrote x there, I meant y. I'll come back and fix it now. Okay. Okay, it'll still be e to the 0, and it'll be minus 2 times minus 1, so also 2. So my plane equation of z minus 1 equals 2x minus 1 plus 2 plus 1. Ta-da, I'm done. There's our plane equation. But we could also multiply out, and we could get 2x plus 2y minus z equals what? That is going to be a minus 2 plus 2, it cancels. Minus 1, if I'm not mistaken. Okay. That's a plane equation. Easy, right? Going to try number 91. Okay, differentiability. So what I'm going to be doing in the next little section is I'm going to be taking the single variable definition for differentiability. I'm going to be interpreting what that means in a diagram to do with distance between functions and tangent lines. Then I'm going to step that up a dimension and think of it in terms of, instead of curves and tangent lines, thinking of it in terms of surfaces and tangent planes. And then I'm basically going to take that same diagrammatic definition of differentiability and rewrite it for a two-variable function. Okay, so it's not a proof at all. It's a justification. It's a justification for that rather beautiful expression that's in the box on page 31. So there we go. In R2, a function y equals f of x is differentiable at a point if that expression is true. The limit of f of a plus h minus f of a over h is the derivative. And I can rewrite that to that thing over there, where all I've done is I've brought the f dash across and I've brought it into the inside the limit and into the fraction, if you will. Okay, that thing in the brackets is the linear approximation to f of a plus h. So we can interpret differentiability as, okay, now I'm going to draw a picture. Okay, let me scroll. Thank you, stylus. Okay, so let's draw a picture. Here's some curve. Right. Here's some points. There's A. I'm going to take some points at a distance. I'm going to call that A plus H. Okay. So this distance over here is H. Hello, stylus. You want to catch up with me? No, you're not. So that distance over there is H. Okay. I'm going to write this height over this distance tends to 0 as h tends to 0. That's what that thing that I've just scrolled past. In fact, let me see, can I have both on the screen at the same time? The thing is at the top of the screen there can be interpreted in the diagram as that little distance, the little distance between the actual true function value of f of a plus h minus its linear approximation. So if you were saying, okay, I've got a curve, I've got a tangent line, and instead of reading my points off the curve, I'm going to read it off the tangent line. The thing you'd be reading off is the thing that's in the brackets there in that expression at the top of the screen. Okay? I hope that that's clear. If it's not clear, then maybe make a little note to yourself in the margin, confirm that this does make sense or something, and sit down and do it in your own time. But that's basically what that definition of differentiability is saying. The numerator is that little distance, and the denominator is that little horizontal distance, and the definition of differentiability is saying that the ratio tends to 0 as the denominator tends to 0. Okay? Okay, I'm going to stop there. And then in tomorrow's lecture, I'm going to start on this same document from here. Because there's nothing I can say in a short time. I'd either have to go 10 minutes over the lecture period or stop now.